As you know, I'm always talking about content that I consume when I'm not producing this show or writing one of my books or whatever. When I'm out and about, or just killing time, looking for something to do to improve my thinking. So many of the topics on this show, I am not qualified at all to understand, really, even after reading the guest's book. So I have to be an autodidact, and you should be too. I do that through brilliant.org. Brilliant is the online platform that produces these short courses that are crafted by award-winning teachers, researchers, and professionals from MIT, Caltech, Duke, Microsoft, Google, and more. So when you do this, when you log on, you just touch the app on your phone or on your laptop, open up the program that you want to study, and what you have are these short tutorials. They're just so much fun. It's like playing a game on your phone. And as a consequence, like, you can create programs with drag and drop coding, interact with charts and graphs, and play around with many stunning visualizations. And beyond the technical know-how, Brilliant boosts your analytical thinking skills to make you a better problem solver every part of your life. It's almost like a superpower. So be an autodidact. Use brilliant.org to improve your thinking. Go to brilliant.org/skeptic to get your free 30-day trial and 20% off your annual subscription. So do that, please, as a favor. They are supporting the podcast, which I appreciate, and I would not have them on if it wasn't something I didn't myself use. So go to brilliant.org/skeptic and you get your free 30-day trial plus 20% off your annual subscription. Do that now before you listen to the episode. I'll pause it right here. Okay, boom, now go back and then come back and listen to the show after you subscribe to brilliant.org/skeptic. All right, thanks for listening. Here we go. All right, hi everybody. It's Michael Shermer, and it's time for another episode of the Michael Shermer Show, brought to you by Skeptic Society and Skeptic Magazine. Here it is, still in print, available in fine bookstores everywhere, as well as right here in the Skeptic offices, where you can go online at skeptic.com and order your copy, print or digital. This is the latest issue on energy matters, why we got to go nuclear if we're going to become interstellar, which is a hint to my guest today, who is the one and only Avi Loeb, my friend and colleague from Harvard. Let me give him a proper introduction. Avi is the Frank B. Baird Jr. Professor of Science at Harvard University, the longer-serving chair of Harvard's Department of Astronomy, the founding director of Harvard's Black Hole Initiative, and the current director of the Institute for Theory and Computation within the Harvard Smithsonian Center for Astrophysics. He also heads the Galileo Project, of which I am a member of that team, and he chairs the advisory committee for the Breakthrough Starshot Initiative and is former chair of the board on physics and astronomy of the National Academies. Author of 8 books and more than 1,000 scientific papers, Loeb is the elected fellow of the American Academy of Arts and Sciences, the American Physical Society, and the International Academy of Astronautics. In 2012, Time selected Loeb as one of the 25 most influential people in space. I don't know about terrestrial, but in space, I guess, incorporates that. Anyway, he lives near Boston, Massachusetts. He was on before for his book, Extraterrestrial. Here's the new book. It's called Interstellar: The Search for Extraterrestrial Life and Our Future in the Stars. Beautiful cover. I just finished it this morning on my bike ride on the audio edition. Avi, nice to see you again.
Great to see you, Michael.
So I understand. So we're just a heads up to our listeners. We're recording this on August 24th. You have a big, and the book comes out next week. And then on the 31st, you have an announcement you're making, or a declaration, or I don't know what it is. You have a paper coming out, or what's going on? Tell me.
Well, it's the practice of science. And I think we both share the view that we should be guided by evidence. And when I went to the Pacific Ocean to collect that evidence, it's all materials related to the first recognized interstellar meteor that the U.S. Government satellites spotted back in 2014, almost a decade ago, over the Pacific Ocean. And it was moving very fast, this object. In fact, faster than 95% of all the stars in the vicinity of the sun outside the solar system when we extrapolated the US government measurements. And moreover, it maintained its integrity down to the lower atmosphere, meaning that it was actually tougher than all 272 space rocks that were cataloged by NASA over the past decade. And so it raised my curiosity as to whether it may be a Voyager-like meteor. Just imagine Voyager that we sent out of the solar system colliding with a planet like the Earth in a billion years and appearing as a meteor. It would have material strength unusual relative to all the rocks, and also would be moving faster than usual because of its propulsion. So I was set up to collect that evidence. And we can talk more about the process by which the materials were collected, but the bottom line is we retrieved them and brought them back and used the mass spectrometer at Harvard University to figure out the composition. And the breaking news is that we found spherules. These are molten droplets from the surface of the object that were produced when the object was exposed to the immense heat from the fireball that it generated as a result of its friction with air. It was 3% of the Hiroshima atomic bomb energy released into 500 kilograms of material. So it melted, and we found those millimeter-sized marbles at the bottom of the ocean at a depth of more than a mile across a region that was 7 miles in size, which sounds like a very challenging task, but we managed to do it, and we can talk about the details. The point is, now we analyzed those spherules. We found 50 on the ship, and then my summer intern, Sophie Bergstrom, found 650 more from the materials that I brought to Harvard, and altogether we have more than 700, and we analyzed them, and we found a concentration along the meteor path. So there was a higher yield of spherules per amount of mass retrieved close to the meteor path, which indicates that indeed we were at the right place. So we had also control regions and saw an enhancement close to the meteor path. And we found a very unique type of spherules there that cannot be found in any control field far away. And I can explain the details of what makes them unique, but the bottom line is the materials that they are made of is different from solar system materials. So let me summarize in one sentence.
Yeah,
it's
please.
the first time that humans put their hands on materials from a large object that came from outside the solar system.
Okay, so that's the announcement.
Yes, and I can go into detail.
Yeah, we can do that in a second. But as we were getting on here, you mentioned the New York Times Magazine has a big story. Is it about this subject?
No, because the story came out today, and I told the reporter that we will have the results next week. And obviously, the story was finalized a couple of weeks ago, so I could not reveal the details at that time, and it's outside the scope of this story. But as it turns out, this story focuses mostly about the human part of the pushback that I get from doing my work. And by now I decided to take the approach of an eagle. An eagle very often has a crow on its back that pecks at its neck, and the eagle solves the problem not by pushing off or fighting with the crow. The eagle just rises to greater heights, and then the oxygen level is lower there, and the crow just drops off the back of the eagle. And so for me, the greatest heights is doing science as it should be done, collecting the materials, analyzing them with state-of-the-art instruments by scientists that have no bias whatsoever. So in that case, it was Stein Jacobson at Harvard University, very solid scientist, and highly respected worldwide. And, when he came to me and said, this is unheard of, I listened to him. So he had to invent two terms. One is Belau spherules. Now, what are Belau spherules? The composition is enhanced by factors of hundreds in beryllium, lanthanum, and uranium, and also the elements between lanthanum and uranium. And when I say enhanced by hundreds, it's never seen. Something like that was never seen in the solar system before. Okay, so it has to come. It doesn't resemble anything on Earth, the Moon, or Mars, or it has. You can think of natural processes that might do it, and we can talk about them. For example, you can have a molten lava magma ocean a planet made of magma ocean that in which you have differentiation, that those elements that I mentioned are enhanced. Beryllium, I should say, is also a flag for interstellar travel because beryllium is produced by cosmic rays breaking heavier nuclei. That's how beryllium is made. So if you have an interstellar object, the surface of the object is exposed to cosmic rays at a higher intensity than we find in the interior of the solar system, like the asteroids are witnessing. So you will have much more beryllium than in the solar system asteroids. And that's what we see. We see hundreds of times more. And so beryllium may be one independent flag, then the enhancement of beryllium, lanthanum, and uranium, and all heavy elements between lanthanum and uranium. So we call it belau. That composition is unique and never seen before. And the third thing is we see isotopes of iron. You know, iron is the most abundant element in those spherules. So we can talk about it, but some of my colleagues who worked on space rocks for decades, on the day that I came back from the expedition, there was a paper accepted for publication in the Astrophysical Journal by two of these experts saying, we tried to fit the US government data with a model that is used for describing stony meteorites or iron meteorites, and we can't do it. Therefore, the government data must be wrong. They measured the velocity to be 3 times higher than it actually is. If we lower the velocity, the speed of the object by a factor of 3, we can fit it with our model for stones, stony meteorites. I call that the Stone Age of science, where everything in the sky must be stones. So if the data shows otherwise, you just say the data is wrong. And by the way, we know that most of the universe is not made of stones. It's made of dark matter. We've never witnessed it in the solar system. We call it dark matter because we don't know what it is. And to claim that if data does not agree with a model for stones, therefore the data is wrong, it's very arrogant. And at the time that they published this paper, I should say, I held in my hands those spherules that are made mostly of iron, and they were concentrated along the meteor path. So what I'm trying to say is that the method of science is not always followed by people who call themselves scientists. In other words, they would rather say the data is wrong, not search for evidence, and argue that if their model doesn't fit the data must be inappropriate. And I should say that the government who measured, the government agency who measured this data is the US Space Command. And they are responsible for national security. They're getting more funding than NASA. And to claim that, they issued an official letter saying at the 99.999%, this meteor is interstellar. And what the astronomers are saying, no, you don't know what you're talking about. So aren't they worried about taxpayers' money going to an agency that doesn't know what they're talking about? Because they wrote an official letter to NASA confirming that it's interstellar. And what I say is I went there and I found it, and therefore I sleep better at night because I know that the US Space Command knows what they are talking about.
Okay, Avi, as you know, a lot of your critics say you're not following science. So let me ask you this: have you submitted this to peer review yet?
It will be, finding? Yeah. By the time this airs, your podcast airs, it will be submitted to peer review because we are planning that before your podcast airs.
And by that you mean you've submitted it to a journal and they are sending it out? Okay.
No, the regular procedure is you submit it to a journal. In this case, a very prestigious one, and the journal editors send it to usually 2 referees. Yes, and then there is a peer review, and we hear back from the referees and address their comments, any criticism they have. But there is also in parallel, what happens very often is there is an archive of preprints, and the papers are posted there before they are accepted for publication because that allows one to get feedback from the community at large. So we will post it there, and having just 2 referees is not a representative sample of the community because they could be biased, they could miss some important points. So my hope is to get feedback from the entire community.
Okay, good. This is what I've done. So I talked to Peter Brown at Western University And he explained to me, what these spherules are and so forth, and then admitted he's not the world's expert on these spherules
But he
that are on
hasn't
the.
seen the spheres that we collected.
I understand. No one has. This is part of the problem. You haven't shown them to anybody
Right.
outside of your Harvard lab. So I said, all right, who are the world's leading experts on this? So he emailed me their names, phone numbers, and emails. So I emailed them, and they emailed me back. Not all of them. There was 6 of them, and I got, would you like to hear what they said?
No, because they don't have access to the materials. How can they say anything?
Well, okay, just in general about these
Oh,
spherules.
okay.
Because,
Generally, they exist everywhere on Earth, of course.
yes.
No, so that's what I wanted to explain.
But Avi, let me give you some feedback. If you're curious what your colleagues think, people that are in a position to know, not me, what do I know, but what these experts on this subject say. Now, so Michael Zelensky of NASA says, yes, I know all about this, but I would rather withhold any question or statement until I see what he actually has.
Exactly. That's the right approach. Yeah.
Okay, Matthew Genge, Genge, and maybe.
Yeah, he's an expert. Yeah. Mm-hmm.
Yeah, Imperial College London. Yes, I'd like to see the paper. I'm guessing it won't be in Nature or Science. However, I do think pushing the envelope is necessary as a scientist, as is being provocative. But at the end of the day, the more dramatic the conclusion, the stronger the evidence has to be.
Exactly.
However, I haven't seen the data, thus I can't give a proper opinion.
Excellent. No, I completely agree with both.
Yeah, but let me continue. So here's my question for Avi Loeb. This is him. The only evidence universally accepted by scientists for an origin beyond our solar system is an isotopic composition significantly outside the range of materials within our solar system.
We did that.
What isotopes have you analyzed in the materials you have recovered? What is their range as a ratio to maximum solar system values?
Yeah, that's excellent. By the way, both of them say very sensible things. And that's exactly what we have done. We analyzed the isotopes of iron, because that's the most abundant element in those spherules. And we compared it to solar system materials. So you will find the answer to this question in the paper.
Okay, good. He says, considering radar observations are highly uncertain, how can you be certain that this meteor was interstellar?
Excellent.
Many meteor scientists claim there still has never been an unequivocal interstellar meteor.
Right. So the criticism here, which was mentioned also in the paper by Peter Brown, was that radar systems are not reliable, especially when operated by the US government. The point is, in the data itself, it says that it was US government satellites. Okay? So it's not radars.
Okay, so it's when you talk about the Space Force tracking this, it's by satellites, not ground-based.
I mean, I was surprised to see that, but in the light curve, when I looked at the light, when this criticism came up by Peter Brown a couple of months ago, I checked the data again, and I saw the heading of the light curve of the fireball said satellite data. Okay? So, as I say, people are guessing what instruments were used, but it's not radars only.
Yeah.
I mean, maybe radars were used as well, but it's in addition satellite data.
Okay. He has a final point here. And again, I'm quoting from Matthew Genge. If you heat I think Ti rich, is that titanium rich?
Titanium, yeah.
Metal in an oxygen rich atmosphere, it reacts to form titanium oxides.
Right.
It is difficult to say since the results haven't been published, but if your particles are made of titanium rich metal, then they haven't experienced atmospheric entry.
That's right. Excellent point. By the way, I'm really pleased. They make it's perfect. I wish the New York Times Magazine reporter would have spoken to these scientists, because they really say everything that is important. So one result that we got was that the so-called volatile elements that can be lost as a result of evaporation during the fireball phase, are indeed missing in those spherules. So that demonstrates, irrespective of whether they come from the solar system or interstellar, it demonstrates that they came from an object that passed through the atmosphere and had a fireball, because those volatiles are missing. And that distinguishes between spherules that may have been made by geological activity here on Earth, okay, from ones that come from space. So excellent point. We looked into that.
Yeah. Okay.
I should say all the points are excellent. Everything said is relevant and
here's a final point here I think you might enjoy. I do, however, agree with Avi. If an alien civilization ever visited Earth, now or in the distant past, they may have left tiny pieces of evidence on our planet in the form of droplets formed by their atmospheric entry. The evidence, however, must be exceedingly strong. For example, several years ago, we found iron manganese oxide spherules in 100-million-year-old seafloor rocks, and it crossed our minds that these materials are used in spacecraft alloys. However, it turned out that the ordinary interplanetary dust is transformed during its time on the seafloor by replacement of nickel by manganese. Geology is a complicated business, as we still don't know all the processes that operate.
True. Completely true. So here is my ask for you, Michael. If you just send me the email addresses of those people, I will recommend them as the referees because they sound completely
I'll do
professional.
That. Yeah, of course. Oh, they all
Unlike
want to
those
say
people that were quoted by the New York Times Magazine, these guys are completely professional, and I salute you for selecting them because they are mentioned in the reference list of our paper, the names that you mentioned, but I just need their email addresses so that I can recommend them to the editor of the journal that we submit the paper to.
Yeah, good.
Because
I'll do that.
Their points are fair and exactly touch the important aspects of the challenge here.
Okay. Would you like to hear some more? Because it's super interesting.
Yeah, go ahead.
George Flynn from SUNY Plattsburgh. Cosmic spherules have been recovered from the ocean floor since the Challenger expedition in the 19th century.
True.
Since the Challenger expedition recovered these spherules, they have also been recovered from lakes, even the polar ices, and so on. So I guess the most important question for you is, how do the spherules Loeb recovered differ from the ones routinely collected and identified over the past century and a half? And what characteristics distinguish them from the spherules of likely solar system origin?
That's exactly the subject of many of the figures we have. Exactly that. And I should say, Michael, so that you will understand the context, when we go to control areas, that's nothing to do with the meteor, okay? So we go far away. And also in the vicinity of the meteor path, there are regions that, are not associated with the meteor. So even along the meteor path, it's a mix of the meteor spherules plus the background. And we have a lot of background, okay? Because we see spherules that belong to solar system origins, okay? So it's an excellent point, and we address it because the Belau spherules that I mentioned have a very distinct abundance pattern that is completely different than.
How are you spelling that, Belau? How are you spelling?
Okay, beryllium, lanthanum, and uranium. So you just take the initials that represent the elements. Be represents beryllium.
Yeah.
La represents lanthanum.
I see.
By the way, lanthanum looks like a silvery metal. I don't know if you've ever seen that. And then uranium, is mentioned in Oppenheimer's, the movie Oppenheimer. And
Belau. Gotcha. Yeah. Okay. Interesting. I think the important point is that extraterrestrial metallic spheres have been collected from the seafloor in numerous locations. I was stunned to hear that there's like trillions of these little grain-sized things.
Definitely. Yeah.
So it's a signal detection problem. You scoop up a gazillion of these things. Which ones are natural? Which ones are...
That's exactly right. So that's why we check the composition to tell us what is background and what is unique to this meteor. And that's we found a lot of background spherules, as he is pointing out. That's everywhere. And there is a special type never seen before. That's the whole point. That, what Stein-Jacobson had to invent are two terms. One is the Belau composition pattern, and the second is these spherules. These spherules, that classification never appeared in the literature. It means differentiated from a magma ocean or some other source, a spherule that has a very different abundance than you find in, on the Earth or the Moon or Mars. So anyway, all these points are well taken. Yes.
Yeah. Well, continuing, I also talked to Don Brownlee, who is apparently the godfather of microspherules.
I have great respect for him, yes.
He says, my thoughts are that most interstellar solids entering the solar system in sizes of microns to kilometers were probably made during the peak of star formation in the galaxy and are over 10 billion years old. These objects have typically spent billions of years in interstellar space at near zero temperature. No heat for Captain Kirk or semiconductors. The first interstellar solids entering the solar system on unbound orbits were found by dust detectors on the Ulysses and Galileo spacecraft.
Correct.
If an object is ET made, it will surely not be made of transparent aluminum or other fantasy material. It would be made of materials that could be used to make spacecraft. The materials that we use to make spacecraft are exotic materials that would never be expected to be found in natural planetary materials, like metallic Al aluminum,
Yes.
metallic Ti titanium, carbon fiber,
Yeah.
Kapton sheet with Kapton sheet with metal coating, gold connectors, high strength steel, Teflon, copper wire, epoxy, and a vast array of engineered materials that would never have existed without human or ET production.
Okay. Yeah, that's. By the way, you notice that I mentioned the conclusion that it came from outside the solar system, which is a robust assessment based on the composition and the isotopes, the issues that were brought up. The one thing I didn't mention is whether there is any hint of technology, and that is a question that we don't address in this paper. Because
Okay, so
it requires more analysis, and also I should say it would be much easier to figure it out if we found a big piece, which we could do at a future expedition.
That's what I told Chris Mellon when you were gone. I said, I hope Avi brings back the dashboard, the Millennium Falcon or something.
Well,
it's really obvious.
The problem is we didn't have the machinery to do that. What we designed is a sled actually based on Brownlee's past work. He was a pioneer. He used the magnetic rack. And we built a sled with a different design than he used, with magnets on both sides. And it worked. And we collected all these magnetic spherules with it. And we looked for the unusual ones that were never found before, exactly along these lines. And yeah, so I agree.
Yeah. Let's see. Yeah, maybe I've covered enough of this. Steve Desch at Arizona State. I gather you've collided with him in the past over issues like Oumuamua, I think.
No, I can tell you one story about him.
Yeah.
Okay.
His response was, let's just say, a little on the spicy side.
I know, but let me explain that I was invited to give a lecture back in April at Arizona State University. And it was by Paul Davis, a very highly respected physicist.
Yeah.
And I said, of course, yes, I'll be delighted. And then half a day before my lecture, I was told by Paul that actually it will be Stephen Desch that introduces me and challenges me and moderates me. And I said, no, thank you. My experience was very bruising with, I just don't feel safe in his company because he's very aggressive. So I said, okay, in order not to disappoint your audience, why don't you ask him to speak instead of me about Oumuamua and interstellar objects? So he said, sounds good. And then Steve Desch gave a talk about my subject. Okay? And that was videotaped.
Oh, now, you didn't go?
No, I didn't.
Wow.
And so he gave the talk. I gave him the full stage. And in the talk that was recorded on video, he said, there is no chance whatsoever that Avi Loeb will find anything in this expedition because the region is 7 miles in size and looking for millimeter-sized droplets is hopeless. Okay, he put it on record. Then I went there and we found something, okay? So someone came to me, a documentary filmmaker came to me and said, it would be nice now that we have the results that you brought back from the expedition. It would be nice to have a video clip of someone who said that you will not find anything next to it. And I said, great, it's all on videotape. So here is my conclusion. Bullying has a price.
Wow, okay. He makes one point. I just thought maybe you've addressed this already. He says, everyone agrees that if the meteor entered at the speed of 45 kilometers per second and vector reported in the CNEOS database, it would be interstellar, but no scientists trust those numbers, and it's very likely this meteor came from our solar system. I think you addressed that already,
when he says
right?
no scientist, he is excluding the scientists within the U.S. Space Command, which check the data. They have access to the classified data, and they confirmed it in an official letter to NASA. So they took time out of the day job, which is national security related, to promote blue sky science and support the fact that it's interstellar. They wrote this letter. It took 3 years to produce. And now Desch says, I don't believe you. And I say, I believe them because they looked again into it. And I went there and I found the stuff. So, and we found extrasolar composition never found before.
Okay, so just to be clear, no one has seen this classified data of the object coming in from out of the solar system because it's classified. But the people that could look at it told you, yes, it's
They wrote an
overwhelmingly
official
likely to
letter.
be.
Yeah.
Okay.
It's not just
All right.
telling, I mean, obviously the NASA catalog included their data, but they went into the effort of writing an official letter to NASA stating this conclusion at the 99.999% confidence.
Okay. And finally, just before we get off this subject, this BLAU composition of the microspherules that you brought up from the bolide could happen naturally, or are you claiming
definitely.
you're not claiming it indicates
No. So let me talk. That's an excellent point that you brought up. You can make such a composition in a magma ocean. It's called differentiation. So if a planet has an iron core, there are some elements that have an affinity to iron, that love to be chemically associated with iron. And when you have a magma ocean, everything is molten, those elements sink towards the iron core. And you end up having other elements differentiated from them. And these are the elements that are prominent in the BLAU spherules. The beryllium is more to do with the passage through interstellar space with cosmic rays, as I discussed before, but the other, lanthanum to uranium. So that's a natural way of getting it. The challenge is mainly, and again, I'm just speaking completely agnostically here. The challenge is that you calculate the rate of impacts on Earth. So such a meteor is seen once a decade, meter-sized meteor from interstellar space, because the NASA catalog was over a decade. There was one object, there was a second one. So roughly once per decade, they collide with Earth. We know the cross-sectional area of the Earth as it moves around the sun. And you can calculate the needed number of such objects per unit volume such that the Earth will intercept one of them every 10 years, okay, once per decade. And that tells you that there should be millions of these objects within the orbit of the Earth around the sun at any given time, so that once per decade we will bump into one of them, okay? And so that's a large number. And if you extrapolate it for the entire size of the solar system, the number ends up being 10 to the power 23.
Wow.
So the bottom line is there should be 10 to the power 23 such objects produced, meter-sized object, 500 kilograms or so in mass, produced per star in the Milky Way galaxy, in order that at random, we will bump into one of them every decade. So that's a big number. 10 to the power 23 of 500 kilogram objects implies that you need a full Earth mass in those objects per star. So what you need is to shatter an Earth mass planet into 500 kilogram bits. That's the equivalent of what you need to do. Now, it may be possible, but you need to do it with a magma ocean. Okay, so it cannot be just rocks that are used as Lego pieces to build up a planet. What you want is to have this differentiation that I was talking about first in a magma ocean, and only then, whatever the product is of this magma ocean, that is the thing that you shatter into 10 to the power 23 pieces if you have an Earth mass planet.
Yeah.
So it's possible to do naturally. I'm sure there will be papers trying to find scenarios. There is another possible route that is natural, and you can produce these elements by having a collision of two neutron stars. A neutron star is, the core of a massive star that collapses, a star weighing somewhere between 8 and 25 times the mass of the sun, collapsing to an object that is at a density of a nucleus, an atomic nucleus, but the size of a city, like 10 kilometers, 12 kilometers in size, in radius. And that kind of neutron star is very compact. And when two such neutron stars merge, some neutron material gets ejected, and then that turns into those heavy elements.
Hang on, Avi. I lost the thread there. Is this explaining this Belau composition, how this could have come about?
Yeah. So
Okay,
you
I see.
can, what I'm saying is the heavy elements can be made out of neutron star mergers.
I
They
see.
could also, but it's not all of them. It's just there is a fraction of them. And then the other fraction has to be made by some stars that are called asymptotic giant branch stars. And so, you need the combination of astrophysical sources if you don't want to do it in a molten lava, magma ocean. If you want to do it otherwise, that's the second route.
Okay.
And of course, there is always a possibility that maybe it belongs to something more exotic. But in the paper, we don't go into that
By
in
which you
detail.
mean an extraterrestrial civilization. I mean, if Voyager escapes the sun's gravitational pull, which it will, it's on its way to leaving, and it ends up at some other solar system somewhere. That's what you mean. It could have been
Yeah, exactly.
intentionally. Otherwise, how would an object escape its own solar system? What
Oh,
natural force would
that's a
do
great
that?
question. So the processes that do that, for example, if the solar system extends halfway to the nearest star, okay, and
Yeah.
the outskirts are called the Oort cloud. It contains all these building blocks that were used to make the planets, the rocky planets like the Earth. So just like Lego pieces, and they were left and kicked out to this sphere, the Oort cloud that surrounds and it goes out to about 100,000 times the Earth-Sun separation. So the Oort cloud is really far. And the easiest, and the objects in it are loosely bound to the sun because they're so far away, 100,000 times the distance of the Earth from the sun. So they move very really slowly and are easy to dislodge by a passing star. So the most common interstellar objects that you would expect are originating from the outskirts of a solar system like entity, and when a star passes by it, through the force of gravity, it can dislodge some of those objects. That would be the most natural. But then there could be other processes when in the early days when you make in the infancy of a planetary system, when you make the planets, you start with small building blocks and they can scatter each other. You can basically scatter objects out of the solar system. And then you get to the question of how can I envision a technological object similar to Oumuamua that I suggested may be pushed by reflecting sunlight. So it had to be very thin. And there, I wrote a recent paper about a year ago about a piece of a broken Dyson sphere. So a Dyson sphere, Freeman Dyson, about 60 years ago, had the idea that an advanced civilization may construct a megastructure around its star so that it can harvest the energy output from the star. Because we on Earth, even if we attempt to produce as much clean energy as we can, we are harvesting at most the amount of energy that is intercepting the Earth from the sun. And that's a really small fraction. 10 to the minus 8, 1 part in 100 million of the energy coming out of the sun is intercepted by Earth. We cast a very small shadow. But if you surround the sun with a sphere that has the orbital radius of the Earth around the sun, you can get most of the energy. And that is the Dyson sphere. And engineering-wise, it's very difficult to build a rigid sphere. So there was this idea by Robert Forward, who was a science fiction writer, that perhaps it's made of tiles that are solar sails. I mean, they're basically held against gravity by radiation pressure from the star, so they're just hovering like kites. And you tile them and make a Dyson sphere out of that. But the one thing to keep in mind that Forward didn't think about is that the star evolves and eventually becomes brighter. And when it becomes brighter, it will push out those tiles, break open this megastructure, and you end up with those sails going into interstellar space because they were almost unbound to start with. They were just hovering. So it's very easy to dislodge them by the star becoming brighter. And I said, okay, well, maybe Oumuamua was thin because it was a piece of a broken Dyson sphere.
Wasn't there an observatory looking for signatures of artificial, of Dyson spheres?
Yeah.
I forget who was doing that.
It's not it's not just a specific observatory. It's we have data sets, and the signature of the Dyson sphere is that, it takes the energy that the star is producing. But the sun, for example, has a temperature of about 6,000 degrees on its surface, roughly speaking. And the luminosity, the amount of energy emitted per unit time from the sun, is related to its temperature and the surface area. But if you build a sphere that is 100 times bigger than the sun, which is roughly at the orbital distance of the Earth from the sun, it's 100 times bigger. So the surface area is 100 squared times bigger than the surface area of the sun. So it's altogether 10,000 times bigger. Turns out that the temperature will drop by the square root of the distance. So because the luminosity is preserved, and the luminosity scale is as temperature to the fourth power times the radius squared. So the temperature will drop down by a factor of the square root of 100, factor of 10. So you end up having a temperature of around 600 degrees instead of 6,000 degrees. And that kind of temperature emits mostly in the infrared. So the idea was, let's search for, stars enshrouded in some enclosure that emits in the infrared at the right temperature. And such systems were found. It turned out to be dusty environments of stars. So, and then there were ideas that, maybe some civilizations may use not just the stars, but that they are near to, but maybe the entire light from the galaxy. You can put limits on that, because Kardashev thought some very advanced civilizations will use all the energy of their host galaxy. And by the way, in my book, I talk about a completely different scale of civilizations. We can talk about it.
About 1 second. So I remember that story from a couple of years ago, Gabby's star, where there was a dip in the light curve from the star, and it looked like it was an object going around it, and it was it didn't match another planet or comets or whatever. So there was some talk that maybe it's a piece of a Dyson sphere blocking the sunlight or something like that.
Right.
I remember when the day that story came out, I was on this a KABC radio in Los Angeles. John and Jillian had this drive time talk show at the time, and so they asked about this, and I didn't know that much about it, but immediately Jillian goes, so it was like 1,500 light years away. So what are they like? I'm like, what is who like? The aliens. So this brings up the question of the media, Avi. I mean, they jumped so quickly from here's this anomaly to we have evidence of the aliens.
I know. And the dynamics is driven by the following. That's my assessment. You can correct me if you think otherwise, but basically they get paid based on the number of clicks. And therefore, so very often what you see is the title of an article saying one thing, but the content saying something else. And I found it very frustrating because, in any interview, including the one now, I say the same things, and then I see these stories coming out unrelated, and people come to me and say, but that's not what you say. And I say, what can I do? And by the way, it's not just, I spent 4 hours. It's not just tabloids or journalists you can't trust. I spent 4 hours on fact-checking of this New York Times Magazine article last Friday. And after that, they contacted me several times more while I was traveling. So I spent a few more hours. So you might think, they got everything right. Well, it turns out that the reporter, when I spoke to the reporter, he would ask me about the subject, and I would answer it as professionally as I can, giving all technical details. But the reporter wanted to just chase negativity and would pick up. If I said something that cannot be used in a negative context, he would ignore it. He didn't mention it. And that's another approach. So in a way, he can claim, I'm not lying, but what I'm saying is you're distorting my message. Because let me give you a specific example, because that was documented by an email. So towards the end of the process of fact-checking, the time ran out. So he said, please answer it by an email. Everything else was recorded. And I don't have access to that recording, but the email I have access to. So he said, one scientist claims that an equation in your paper omitted the time dependence of one of the terms. And as a result of that, your claim is not correct. And I said, okay, well, here is the paper. It was published in the Astrophysical Journal, peer-reviewed. The term that you are talking about is important by a factor of 1,000,000 relative to the other terms. And unless this coefficient that you claim is time-dependent brings it down by a factor of 1,000,000, which is not, under any reasonable circumstances, cannot be the case. So we considered, it being 1% up to unity. It cannot be 1,000,000. Anyway, the point is, this criticism of it not being time-dependent is completely irrelevant because this term dominates, okay? Because it's bigger by millions. And I explained this to him in a written email that I can share with you. What did he put in the article? He said, there is a criticism from the other scientists, which he quoted in full everything the other scientists said, including insulting me personally. So
wow,
that was included. That was included. And then my part, and my part was mentioned as, and Avi Loeb, when I mentioned it to him, brushed it off.
Oh.
And I said to myself, what do you mean by brushed it off? I explained in technical details. And he didn't include any of those. So you ask, is that a lie? And that comes from a process after fact-checking. And so I say, a journalist can twist things, irrespective of how much barriers you put along the way, because the journalist can just select the parts that substantiate a narrative.
Yeah. I've gone through those fact-checking things where there's some intern that'll call you and say, here are the quotes that that he may or may not include, but did you actually say this? And they read it. I go, yeah, that's what I said. And do you stand by? Yeah, I stand by that. And then you see the finished article, and it's just portions of those quotes.
Exactly.
Which can be pieced together. So it's an interesting sidebar here, Avi. If this can happen with you when you know what's going on, and it's allegedly fact-checked and stuff, what about stories from Ukraine or whatever in the world? And it's the Wall Street Journal, it's the New York Times, the Washington Post, or whatever. You think, well, they got to be. They have fact checkers.
And by the way, I'm a scientist. I'm a practicing scientist. I'm not a blogger or a science popularizer that can do whatever they want. I'm actually a practicing scientist. I'm in the trenches, okay? And if it happens with me on scientific matters related to the work I'm doing, okay, then think as to how much distortion can occur in the context of politics, where there are no hard facts, no measurements, and no equations that you can say this term is 1,000,000 times bigger, and it's just, it makes me very frustrated because, in my book, Interstellar, I really am hoping that we will rise to the occasion and perhaps show a more intelligent facet of our existence by behaving collegially, working together.
Good luck with that.
Yeah, exactly. Good luck with that.
Not going too well. Well, I think this is one of the reasons you're getting pushback from some of your colleagues anyway, that they just see you on TV, and you do a lot of TV. And it sounds like, Avi Loeb, head of the astronomy department at Harvard University, he says the aliens may be out there. And then they cut to you saying whatever you say. And so the outside observer looks at that and goes, what? He's gone off the rails. He's lost his mind. We don't know that there's aliens here because that's kind of how it comes off on TV.
Yeah, but I don't. Okay, what I'm saying is it's a subject that resonates with the public, a subject that resonates with government. I mean, there was a congressional hearing. The word extraterrestrial was mentioned in the US Congress. It's the civil duty of scientists to get engaged with this subject, not ridicule it, not dismiss it, not repeat the mantra of Carl Sagan, extraordinary claims require extraordinary evidence, without seeking the evidence. So the real fundamental point that I'm bringing to the table is that we should be guided by evidence. I'm a theoretical physicist, by the way. Throughout my career, I wrote almost 1,000 papers that were purely theoretical, okay? And now I decided to pursue this subject as an experimental project. So I'm leading the Galileo project, which established an observatory and planning to make copies of it. And I went to the Pacific Ocean, guess what? To collect materials. It's not about talking and talking. And the other people are just talking and talking. And they call themselves scientists, but they don't want me to do what I'm doing. And I asked why. I'm getting funded from private donations. I'm not taking any research money that was allocated to dark matter research. And by the way, we spent billions of dollars in searching for dark matter. Most recently, the Large Hadron Collider was looking for supersymmetry, which was a prime candidate for dark matter particles, and didn't find it. Did anyone say, oh, that was an extraordinary claim that we shouldn't have attended to? No, that's part of doing science. Now you pick and choose, of course, which problems to work on. I would argue that working on the multiverse or on extra dimensions in the context of string theory is more of a waste of taxpayers' money, and yet you have hundreds of people within the theoretical particle physics community engaged in that, doing mathematical gymnastics, and you ask yourself why? Why? Because in academia, the main task is to impress your peers. So you can decide that this is the sandbox. Let's imagine extra dimensions. That's the sandbox in which you can exercise your abilities, mathematical abilities, to demonstrate that you are smart. And getting confirmation from experiments, forget about it. Actually, it's better not to have any experimental test, because it may show that we are wrong. So it's better to feel that you're always right because you're never tested. And you know what? An interesting anecdote. I had breakfast with a string theorist just half a year ago. And I asked this string theorist, who is a very prominent string theorist, I asked him, what is your main contribution, the paper that you are most proud of? And he said, it's a paper about supersymmetry. And I said, of course, you know that supersymmetry was not found by the Large Hadron Collider. And he's still proud of that, okay? And he said, yeah, but it may be just around the corner. So what it reminded me is the Lubavitchers in Brooklyn, in Crown Heights, because they argued that their rabbi will become a messiah when he dies. In fact, they believed it so much that they built an apartment for him in Israel, because he's supposed to come back as the messiah to Israel, and they wanted him to find the toilets. So they built a replica of his apartment in Brooklyn. They believed so much. It still exists there. You can find it. Now, here is the experimental data point. He died.
He died.
Okay? And he never came back as the Messiah. Okay? He never came back as the Messiah.
It's like L. Ron Hubbard. He's coming back sometime.
So there was a conflict between the data and the theory. Okay? The same as with supersymmetry. Now, what did they say? They said, let's just wait. He will come back. Now, I ask you, what's the difference between this religious belief and claiming that your most important paper is on supersymmetry when the Large Hadron Collider did not find it? It's just around the corner. Now, the difference is that we are supposed to adhere to data as scientists, but it's not practiced.
Well, this is my complaint about the UAP and ufologists talking about disclosure. Coming any time now, but it's like, guys, I've been hearing this for 30 years.
That's my problem as well.
Yeah, nothing ever happens. Now, one of your guiding principles of the Galileo Project is that we're not going to invoke new physics and so on to explain whatever these UAPs are.
So
right?
That got me in trouble with the other side, where people want to say, "Oh, we have blurry data, and it could be new physics." And I say, "No, you need exquisite data to claim new physics." And they have a problem.
Well, you make the point that the Large Hadron Collider didn't find any new physics.
Exactly.
Okay, so the pushback I usually get when I invoke that is that quote from whoever that physicist was in your book, who in 1890 something said, "There's no new physics. We're done. We've got it all down now," and then everything changed. So what is your response to that? How do you know that we're not on the verge of a breakthrough of a whole new physics?
Right. So usually it's anomalies. Okay. So if you see something deviating from what you expect based on the known science, okay? And at first, of course, anomalies are denied. They are shoved under the rug. Just like in the case of this meteor, the experts would say, oh, the data must be wrong. And in the case of a one-time event like a meteor, it's very easy to say that because you can go back. But there are many instances in physics where the error budget was enlarged such that it will accommodate the deviation. But eventually, the goal of science is to improve the measurements and repeat them, and then figure out that indeed there is an anomaly here. And the anomaly implies new physics. By the way, particle physics, experimental, is all about searching for anomalies. And the culture is very receptive to ideas. If people say, oh, there was an anomaly, then the theories immediately jump, and there are hundreds of papers explaining the anomaly in different ways. That's the culture I came from when I worked for decades in the study of the universe, cosmology. And the nature of dark matter is not known. And so a lot of people suggested alternatives, and that was a fair game, because it motivates experiments. And then I come to the subject of rocks or objects in the sky. And what I hear is that I'm not allowed to even mention anything other than stones. And, I feel very frustrated because this is a very narrow-minded approach to science, because what you are always supposed to do is, if there are anomalies, you should be intrigued. About Oumuamua, when I had a colloquium at the Center for Astrophysics at Harvard about Oumuamua, which mentioned a lot of the anomalies. And by the way, I didn't discover them. Observers, there are papers in the literature. Each of those papers shows that there is an anomaly, something that doesn't line up with what we know about asteroids or comets. Anyway, there was a lecture summarizing those anomalies. And when we came out of the auditorium, a colleague of mine that worked on rocks for decades said, Oumuamua is so weird, I wish it never existed. And to me, that's contrary to your role as a scientist, because if something is so weird, you should say, that's exciting, let's figure out whether the anomaly is real, and if it's real, let's figure out the nature of the object. That should be exciting, like a kid. You introduced me at the beginning. You could have saved a lot of time just saying that I'm a curious farm boy, because that's what I am.
Well, so the question is, at what point do enough anomalies pile up that a new theory is needed to explain it? So the aberration in Mercury's orbit, for example, is the famous example of Einstein's relativity to explain it, because Newtonian mechanics doesn't explain it. So what would be the current anomalies that would need a new theory or something to explain?
Well,
like dark matter?
Dark matter is one, but I would argue that checking anomalous objects near Earth is more consequential than dark matter, the nature of dark matter, and it should receive similar budget. Okay, so if we invest billions of dollars in the search for dark, we better invest billions of dollars in looking at the sky for objects near Earth. Okay, and seeing that all of them are rocks. If indeed all of them are stones, so be it. But maybe not. So we launched 5 probes to interstellar space. Maybe other civilizations did that. Let's just check. And it's different from searching for radio signals, because radio signals are like a phone call. If someone has to call you when you are listening, whereas here, it just piles up in interstellar space. These are just like plastics in the ocean, because they are bound by gravity to the Milky Way. So the idea is to look for those things, and we haven't done that. Only over the past decade, we discovered the first interstellar objects. So it's a new frontier. To me, it's exciting, and there should be more money allocated to it. Yeah. And if we find nothing interesting, so be it. We move on. The problem with UAP is, on the one hand, you have those people who argue that they had an experience, or including people who claim that they were abducted. I'm not a therapist. I'm not in the business of psychology. I don't care what they say. I want instruments to report back to me. Yeah, and by the way, FIFA in the World Cup, the US soccer team, the women's team, was knocked out because there was data from video cameras showing the goal, the ball passing the line. And it was not, they didn't ask the players, they didn't ask the audience. And the players can say whatever they want. If you have good enough data, you don't need to listen to them.
That's right.
And if you ask me what is convincing data in the context of objects, it's really simple. If you land on an object, or if you go to the Pacific Ocean and you collect a big piece, you can tell if it's a rock or a technological gadget. There is no confusion here. Okay. The only thing that you need to make sure is that it's not human-made. Okay, that's the main thing.
This is my complaint about the. What would it take to prove, this? Well, the Chinese spy balloon would be an example. Everybody could see it. No one talks about the credentials of the pilot that shot down the Chinese spy balloon. Doesn't matter. We could all see it, right?
Right.
And then another point that David Grush talking about, non-human biologics. So I posted on Twitter just a little bit ago, here's a picture of a non-human biologic.
Yeah. No, so he meant pilots. But
Yes, I
again,
know. I know.
the issue that I have with his case, it's not so much the content of what he said, it's the fact that he did not have direct
Direct access. Yes. Yeah. Yeah.
access to the evidence. So you can have as many people as you want telling you one thing, but it doesn't mean that it's true. There are lots of people who claim that they are Napoleon.
Oh, I know. I deal with them. I
You
hear
met
from
some
them.
of them. Okay.
Okay, but I have a larger point here on that. You make the point in your book that if we encounter extraterrestrials, they're not likely to be biological, and much less bipedal primates that look pretty much like us, except they have
That's right.
almond-shaped eyes and skinny noses or
That's what
whatever.
I think. Yeah, that's
Yeah,
my
yeah.
expectation. Yeah, exactly.
So, what should we be looking for even beyond that? I mean, could you get information on a laser beam or something like this? You don't even need
Ah,
a tiny little chip or.
okay. So first, I wanted to say that when you have a visitor to your backyard, it doesn't make sense to design a committee ahead of time that will tell you the set of rules of how to deal with visitors, because our imagination is limited to what we experienced here on Earth. And the way to deal with a visitor is to first examine what if the visitor is functional device, to study what it's seeking, what is the purpose, and also study the nature of this object. What does it have? Now, you're right that remotely you have limited information. As you say, maybe a laser beam, maybe you can get a good image of it, but it's very limited. It would be much better if the object crashed. Okay, so because then you can bring it to the lab, or if you can capture it, or you shoot it, or so. To me, as a scientist, I'm like a kid. When a kid sees an object, the kid immediately runs to the object, starts to play with it, whereas the adult looks at it from a distance and says, "I pretty much know what it is," and that's the wrong approach. By the way, the kid's approach is the right one. So I would love, if there was an object like that, I would love to bring it down and study it in the lab.
Yeah. So I've always supported the SETI program because at least they're listening and trying to find something. But you make a pretty good argument that it's very, very unlikely that the timing of when we just happen to be listening is the timing when that signal goes whizzing by the
Exactly.
Earth.
Exactly. And let me explain also that most of the civilizations that preceded us are probably dead.
Yeah.
And the reason is simple, because we just have 20% of the age of the Earth to have life as we know it. Did you know that?
Yeah.
Because the sun will become brighter in a
Yeah.
billion
Yeah.
years,
Yeah.
and there will be, it will warm up, boil off the oceans on Earth, and we will have to go somewhere else. So most stars formed billions of years before the sun. So they went through that already. There were lots of tragedies in human history. In cosmic history, not human, but also in human. But in the cosmic history, there must have been civilizations that rose and fell. Those that fell and disappeared and perished because their star evolved or because they had some catastrophe. Those we cannot communicate with, and our only hope is to look for relics. And that's what archaeology is all about, right? There are cultures that used to exist on Earth that are not around anymore, and we can find in archaeological digs the evidence that they existed. And the same way, we can go to look around us in space and see if there are any relics left behind.
Yeah. So let's just off the top of my head, just a thought experiment here. So you roughly get from the primordial soup to us about 4 billion years on Earth. So how many generations since the beginning of the universe could there have been? How long would it be before you'd get the first civilizations? That's at least 4 billion, right?
That's right.
So then 8 billion, 12. So roughly speaking, there might have
So,
been 3 generations of
okay, so just
stellar.
to set the stage, the Big Bang took place 13.8 billion years ago. 13.8. Solar system formed, the sun formed 4.6 billion years ago. Okay, so in between, so the sun formed roughly at the last one third of cosmic history. Most of the stars formed in the last 2/3 of cosmic history. Most of the stars. So the stars that predated the sun could have predated it by a few billion years, and some of them predated maybe by 5 billion years, so that they already went through what we are going through. They already went to the point where the star itself is done, and we see the end result of the evolution of the sun in the form of white dwarfs. And white dwarfs are very abundant. Some significant fraction of the stars with roughly the mass of the sun ended their life.
Yeah. So, but the point is, there's plenty of time for there to be, millions of civilizations in the cosmos, or maybe even a few hundred in the Milky Way galaxy.
Oh yeah.
And that Drake equation very much depends on which numbers you plug in there. And there's some of the components we just have no idea what it would be.
Yeah, but we became technological just in the last century. You see, that's
So,
the issue.
The other point you make that I really like is that the chances of them being at the same level as us, technologically, culturally, is pretty much zero. Right. Given all the contingent steps in evolution to get from bacteria to big brains.
Exactly.
And they're not going to be just a little behind us or a little ahead of us. And we back engineered their spaceships to invent and to create transistors from vacuum tubes. Like, come on, there's no way they're going to be like 10 years ahead of us.
Exactly. So either they are still in the trees of their planet, in which case we have to go there to find them and search in between the branches, which is a very tedious process to find them hanging, from those branches. It's much easier to find those that are much more advanced than we are because they are here. They could visit us in principle. And if they arrive to our doorstep, they are likely much more advanced than us because we didn't arrive to their doorstep yet.
Yeah. I don't know if you've ever crunched the numbers on the Drake equation yourself to see what you come up with. Again, it's so variable. I looked at the literature on that. It's everything from 1 to like 1 million civilizations.
Exactly. So I think it's pointless. And again, I call that talk. You can talk forever. You can argue forever. We have those areas in the humanities where people talk forever. And
the humanities.
No, actually, okay. So here is my point. Humanity, right now in philosophy departments, they focus on teaching the ancient Greeks very often. There is a required class. And my point is the ancient Greeks didn't have artificial intelligence, didn't have computers. We are now developing a technology that would have a great impact on society. And there are many ethical issues to be faced with. And instead of doing humanities of the past, when the reality was very different, we should focus on the humanity of the future and worry about how to mitigate the risks from those new technologies that are emerging like GPT by applying the ethical rules that we developed over the years to those systems, figuring out what should be the way that society deals with those systems and how to avoid the catastrophe, societal catastrophe, which, we brought in the social media to the scene and a lot of mental health problems emerged for youngsters. And we are just playing with fire here because GPT and its future incarnations could really do much more damage than social media did until now.
All right, let's flip the vector here to us becoming interstellar rather than somebody else interstellar coming here. How can we become an interstellar species?
Well, first we have to change our priorities. Right now we are spending $2 trillion a year on military budgets.
Oh, I know.
And I calculated, well, I know that it's not realistic. I'm speaking like a prophet here, idealizing the future. But for example, if we learn that we have a neighbor, maybe it will give us a shock and it would be a wake-up call. That's my hope. And, we are all in the same boat. Okay, the boat is the Earth sailing through space. And we better work together. So if we decide to explore space, we could send a probe towards every star in the Milky Way galaxy within this century. I did the calculation with $2 trillion a year. It's just a matter of priorities. But the second
you're talking about these microscopic, these really tiny spaceships,
right?
Yeah. The little CubeSats.
Yeah, now I'm getting to exactly, CubeSats, exactly. Now I'm getting to the technological challenge, which is how do you make systems that can be autonomous? Because as of now, we behaved like helicopter parents with respect to the probes that we send to Mars, for example. We have the Perseverance rover, the Ingenuity helicopter being managed by engineers in the Jet Propulsion Lab in Pasadena, close to where you are. And it's helicopter parenting, literally speaking. They manage a helicopter. And this cannot be done when you send something to another star, because even the signals of light take 4 years to reach the nearest star system. And if you talk about the typical star in the Milky Way, it will take thousands of years. So you can't have the probe waiting for guidance for thousands of years. And it makes more sense to send a probe that is autonomous. And by the way, nature did that, because when you have the dandelion flower, when it sends its seeds in the wind, it doesn't have an umbilical cord connecting it to the seed and telling the seed what to do at every point. The seed is autonomous, and it lands somewhere on a fertile ground, and it brings the DNA, the genetic making of the dandelion, to make more dandelions. So you can imagine us imitating nature in this way, sending probes that can self-replicate, have 3D printers, but also have a brain, like artificial intelligence astronauts, AI astronauts. And we don't have that as of yet. We never launched AI systems to space as of now, but we might in the coming decade. That's the way I see it. It needs to be the case for interstellar travel, because you want your system to think when it encounters challenges that were not foreseen by the senders. So you want AI astronauts. So we need to develop that technology of launching AI systems to space, because I don't think biology can serve that purpose, because there is bombardment by cosmic rays. They destroy a significant number of cells in a human body after a few years of exposure in space. That's why I don't wish Elon Musk to die on Mars. He needs to go to a cave there to be protected from those cosmic rays. And so sending...
Aren't there shells of, like, if you just have water or urine or whatever that surrounds the habitat, that's enough to protect you from the cosmic rays?
Well, so the best is actually there are these lava tubes that you find in Hawaii. I don't know if you ever went into one.
I have.
So there's, there are the result from molten lava that is flowing, and then the crust freezes on top. So there is a crust, like a ceiling, and then the rest of the flow continues, and you end up with a cave underneath. These are lava tubes, and they exist on the moon and also on Mars. Now, going into a lava tube is the best strategy, because you are protected from cosmic rays by the crust, and moreover, you are protected from the extreme variations in temperature between day and night, which are hundreds of degrees. So my way of settling on Mars is going into the caves there. We started in caves here on Earth in prehistoric times. So I want to check, by the way, Mars lost its atmosphere about 2 billion years ago at the middle of its life. And I want to check those lava tubes and see if there are any prehistoric wall paintings there, because maybe someone lived there, 3 billion years ago. Maybe that requires just intelligent life to be accelerated by a factor of 2 relative to Earth. So at the middle of its life, if Mars had intelligent life, we should find wall paintings.
Yes, well, maybe. Remember the Mars rock from 1996? And to what extent that thing had little microscopic life forms on it.
Oh, yeah, that was a fiasco in the White House. By the way, that set back, I should tell you, psychologically, it set back NASA, because now they're extremely worried about making any statement about anything to do with life, to the point where they never took a drop of water and dropped it on a Martian soil to see if anything comes to life. They never examined a piece of ice, water ice, on Mars.
I thought the Viking spaceship that landed, it scooped some dirt and mixed chemicals in it or something like that. Sagan was part of that team.
Not a drop of water. They never took a microscope. The obvious things, like if you ask a kid, what would you do to check if there is life on, like you would drop no, so they are extremely methodical. They decided about a set of rules, how to decide if something is a form of life and so on. But they should have done just the obvious things, a drop of water, or take a piece of the ice and melt it, because we found worms, in the permafrost of Siberia, and they were rejuvenated, and then they lived after 46,000 years. Okay. Yeah. Now, I don't know if after a few billion years anything would live, but it's possible that the ice contains some biological material, and it's worth checking it. That will be non-human biologics.
Yeah. But the idea is that it's much cheaper and faster to just send robots than humans. Although, see, the one argument is that, well, it's in our nature. We left Africa, we populated the Earth, so we got to leave the Earth and so on. But a lot of my particularly politically liberal friends say, look, that would cost so much money. We have problems on Earth, poverty and so on. We got to solve these problems. Send all the robots you want, keep it cheap, but don't send people.
Well, the issue with people is that you're risking their lives unless you provide them with a habitat. That's my issue. Otherwise, I'm sure you will have a lot of volunteers, and you can think of it as Australia was for the prisoners that the UK sent out. I mean, they thought that they're punishing them, and Australia ended up being a heaven of sorts, and they were very innovative because all of them were, people that were punished for stealing a handkerchief or something. And I mean, there are lots of people that, you might send some politicians that you don't like to Mars.
All right. How do we stair step out of the Earth to the moon, to the planets, to the moons around Jupiter and Saturn, and then out to the nearest stars? And then from there, you get to the arm of the Milky Way, eventually the whole Milky Way. How do you get to another galaxy? I mean, those, it's just.
Well, okay. So that is a question that I was asked in May 2015 in my office at Harvard. A black limousine stopped in front of the Center for Astrophysics, out of which came Yuri Milner, an entrepreneur from Silicon Valley. He stepped into my office, sat on the sofa, and said, Avi, would you like to lead a scientific project with the objective of sending a probe to the nearest star system in our lifetime, meaning within 20 years, because we are at the same age? And I said, well, I have to think. Of course, I mean, I would be delighted to think about it, but I need to figure out how to do it. And I said, I need 6 months in order to come up with a recommendation with my students and postdocs. And I worked for 6 months with my student postdocs, and we found only one way to do that. To get to the nearest star in 20 years means that you need the spacecraft to move at a fifth of the speed of light, because the distance is 4 light years. And so when it became clear to me what the method should be, I was in Israel at the time for the holidays, and got a phone call from Yuri's assistant that he wants me to present the conclusion. And I said, well, okay, I'll prepare it, but I'm going out to a vacation in a goat farm. And we came to the goat, because my wife wanted to go to a goat farm that weekend. And we got to the goat farm. There was only internet, at the reception. So I sat at 6 a.m. the following morning with my back to the office and looking at all these goats that were just born the day before, and composing my PowerPoint presentation. And I'm sure that the owner of the goat farm never imagined that the first interstellar trip would be contemplated in that goat farm. But anyway, a week later, I was in Palo Alto presenting the plan, and we ended up, Yuri was excited, and then we spent months just going back and forth about all the issues. And the method has to do with a light sail, basically a thin membrane being pushed by reflecting light. Okay, and just like when you play tennis, you feel when you hit the ball, the racket bounces back. Okay, so just think of particles of light as the tennis ball bouncing off the sail, which is just like the racket, and giving it a push. And of course, you need a very powerful light source, in this case, a laser of 100 gigawatt or so, and the sail cannot weigh more than a gram or so. And then within a few minutes of it shining on a sail that is roughly the size of a person, that the sail over a few minutes will go a distance that is 5 times the distance to the moon and reach a fifth of the speed of light. And it's just like a bullet. If you shoot it in the right direction, the idea is that it will go the distance, and then you can do that every day and have many spacecraft going in the direction of Proxima Centauri, for example. So that is a technique if you're not patient. Of course, if you are patient, you can use chemical rockets, and they will take about 50,000 years to reach Proxima Centauri.
Well, why is there a speed limit on chemical rockets? What's the physics?
Oh, that's very simple. It's the rocket equation, okay? You are carrying the fuel with the rocket, okay? And that means the idea is very simple. The way it's propelled is by throwing material backwards. So, it's just like if you were on ice and you had some payload and you threw it backwards, then you will move forward on the ice. Okay, that's how a rocket works. You basically ablate some of the mass of the fuel and throw it backwards. That's how a jet plane works. I once was on a jet plane. I did the calculation on the flight and realized that indeed they have enough fuel.
And so good thing.
But the idea is that you throw it back. You can't throw it back much faster than the speed of sound or the thermal speed of the molecules, atoms that you're throwing. Okay, so you throw it back at the speed of sound, and that's limited. So for all the propellants that we use in rockets, it's limited to a few kilometers per second. That's the sound speed, the thermal speed of particles. That when you burn the propellant, that's the kind of speeds of the molecules. You can't throw the gas faster than that. So you end up with a few kilometers per second. And then when you burn a lot of fuel, you can propel whatever remains to a bit higher speed than that. And the rocket equation shows you that you are gaining just a logarithmic factor. The log of the initial mass that you had for the spacecraft divided by the final mass. So that's why rockets have a huge body of fuel. You are left with a payload that is much lighter just to gain this logarithmic factor. But the logarithmic factor doesn't grow very quickly, and the point is you can at most get another factor of 10. So from a few kilometers per second, you can get 30 kilometers per second. All the rockets that we launched to space did not exceed that speed, 30 kilometers per second. That's 1 part in 10,000 of the speed of light. So if you want to move at a tenth of the speed of light, you need to improve that propulsion by a factor of 1,000. You need 1,000 times higher speed than rockets can give you. It's similar to the jump between the Henry Ford T car, the car that Henry Ford invented, the speed of that car relative to the speed of Sputnik. That was also a factor of 1,000. So we need now, in order to get to a fraction of the speed of light, we need another factor of 1,000. And the only technology that allows that is light sails, because you're pushing, first of all, you're not carrying the fuel. So the rocket equation doesn't apply. You're not carrying any fuel. You're pushing a sail with light, so you can reach the speed of light.
But it has to carry like a camera and some computers, right?
So that no problem, because if you look at your cell phone, they can weigh less than a gram. And this technology is already here.
Interesting, right. And the proposed alternatives to chemical propulsion don't require new physics? It's just new technology or new engineering?
As long as you admit that the speed of light is the limit, people talk about wormholes. We don't know how, if they exist. We don't know how to engineer them. It's just a complete speculation. And by the way, I don't enjoy science fiction because it mixes science with fiction. It violates the laws of physics. I was actually at the Washington National Cathedral with Avril Haines and Jeff Bezos in a public forum. And Jeff was saying that he was inspired to establish Blue Origins because as a kid, he loved Star Trek.
Yeah.
And I told Avril Haines, the director of national intelligence, who was sitting next to me because she has a bachelor's degree in physics from the University of Chicago. And I like her a lot. So I said, I never liked Star Trek. And she said, Avi, we have to work on you.
That's right. All right, last two subjects, limits of science and the religious impulse behind searching for extraterrestrials. I was going to read to you an analogy that I got from Sir Arthur Stanley Eddington's book on kind of the philosophy of physics, that you quoted somebody else in your book about the analogy of a fishing net. So here's Eddington's story. Let us suppose that an ichthyologist is exploring the life of the ocean. He casts a net into the water and brings up a fishy assortment. Surveying his catch, he proceeds in the usual manner of a scientist to systematize what it reveals. He arrives at two generalizations. 1, no sea creature is less than 2 inches long. 2, all sea creatures have gills. In applying this analogy, the catch stands for the body of knowledge which constitutes physical science, and the net for the sensory and intellectual equipment which we use in obtaining it. The casting of the net corresponds to observations. Now, an onlooker may object that the first generalization is wrong. There are plenty of sea creatures under 2 inches long, only your net is not adapted to catch them. The ichthyologist dismisses this objection contemptuously. Anything uncatchable by my net is ipso facto outside the scope of ichthyological knowledge. It is not part of the kingdom of fishes, which has been defined by the theme of ichthyological knowledge. In short, what my net can't catch isn't fish.
Exactly. So what you described right now is my life over the past 2 months.
Yes, you were literally in the ocean casting your own net.
No, but I mean also in practice when dealing with this meteor and all the pushback, and I completely agree with this metaphor.
But I mean, you also make the point in your book, that we don't know 95% of the universe. So,
right.
I mean, so much of this is limited.
Here is the fundamental point, the message that the universe delivers, which we should pay attention to. It's that our knowledge is an island in an ocean of ignorance, and that should make us modest. And we tend to brag, to show off with the little we know, and this hubris is unjustified. And nature keeps telling us again and again, you are not so important. Just like with the emperors in ancient Rome, they had a slave whispering in their ear, you are not immortal, you're mortal. And we just forget that, first of all, that we are mortal, of course, but also that we know so little, and that what exists outside the solar system may be quite different than what we find in the solar system. And, this arrogance extends also to us being the most intelligent since the Big Bang, which I find ridiculous. For one reason, that we came to exist as Homo sapiens, humans, only a few million years ago, and that's 1 part in 10,000 of the age of the universe. So just at the end of the cosmic play, and we are not at the center of the universe. So if you arrive late to the play and you are not at the center of stage, the play is not about you. And you better seek other actors who know better what the play is about.
Yeah. One point I always like to make about the possibility of extraterrestrial intelligence is you could get on Earth all the way up to Neanderthals, which is, big brain bipedal primates with tools, but they were not advancing culturally like Homo sapiens did. It's one reason for the possible explanation of Neanderthals. We maybe outbred them or maybe out-tooled them or cultured them or whatever. We don't know for sure. But you could get a civilization a form of life and intelligence as advanced as Neanderthals, and they never achieve radio signals or
by the way,
and so on.
I asked a psychologist who came to my office because he was fascinated by the research I'm doing. By the way, people in other fields are really fascinated by this. So he came, a young fellow, very talented, one of the brilliant minds at Harvard, came to my office and said, and talked with me in general. So I asked him, what made humans different from chimpanzees, when we came out of the chimpanzees? Mm-hmm. And he said, the language.
Yeah. Probably.
And the amazing thing is that now you have those artificial intelligence systems that are language models.
Yeah.
And so once again, we see a transition now with language models that will potentially exceed human capabilities. So it looks like there is a transformation happening now with respect to AI, large language models, which may resemble the way we deviated from chimpanzees. They will deviate from us.
Yeah. Well, that could be, again, one answer to the Fermi paradox, where is everybody? And the other answer is it's a mostly empty space. There's just next to nothing in between the stars. Right. The analogy I learned when I took my one and only astronomy class was, if the sun was the size of an orange in LA, the closest star would be an orange in Chicago. It's just mostly just nothing. So the chances of them finding us are pretty slim.
Exactly. No, that's exactly the point. Even if they exist, it's the vastness of space and time makes it very difficult to find each other.
Okay.
And yeah.
So you write here in your closing passages to your book, you are not alone. Every human knows that somewhere there are or were parents, are or were grandparents, and relatives, are or were other humans. When we apply our reasoning intellect to how unique and individually are we individually are. We grasp an origin story that links us back to the thousands and millions of years to eukaryotic fossils. On Earth, to be unique, incomparable, solitary is not the condition of either humanity or any form of life. I get the sense that, because I've studied this my whole adult life too, the fascination with extraterrestrials. It's almost like a religious impulse, like we're not alone. There's somebody else out there. And if you think about, like a sufficiently advanced extraterrestrial intelligence would be indistinguishable from what we call God, right?
Exactly.
Capable of creating life, engineering solar
Exactly.
systems. Even if
Exactly.
you can get a black hole, a star to collapse into a black hole and a singularity creates a new universe, that's what a deity does.
Right, exactly. And I wanted to add that, Steven Weinberg, in his book, a famous book, The First 3 Minutes, towards the end, he says, the more we know about the universe, the more meaningless it appears. Now,
Yeah.
the reason it appears meaningless to him is because he never considered life in the universe. He was focusing on physical dead objects. And I say, that would bring a meaning to our life. And that's what we should seek. And, when I was jogging on the ship, Silver Star in the Pacific Ocean, there was a filming crew, and the director asked me, you jog every morning at sunrise. It looks like you're running. Are you running away from something or towards something? And I said, I'm running away from some of my colleagues who have strong opinions without seeking evidence, and I'm running towards a higher intelligence in interstellar space.
Nice. That's a good place to end it there, Avi. Thank you so much for talking to me. Thanks for the new book. Congratulations on the new book and for your important work.
Thank you so much, Michael. It was an intellectual treat to speak with you. And
All
I
right.
mean it because I had 3,000 interviews over the past couple of years. This was really special. Thank you.
Oh, well, thank you. I appreciate that.